Hello there, and welcome back to The Sleepy Scientist, where curiosity meets comfort and the biggest questions in our universe get the gentlest treatment. I'm so glad you've joined me tonight. Whether you're settling into your favorite reading nook, lying in bed watching the shadows dance on the ceiling, or simply taking a quiet moment to let your mind wander toward the stars. Tonight, we're embarking on a particularly illuminating journey, one that will take us from the nuclear furnace at the heart of our solar system all the way to the solar panels quietly humming on rooftops around the world. We're going to explore a question that sits at the very intersection of physics, engineering, and human dreams. Could the sun really power everything? Could this ancient ball of fire that has warmed our planet for billions of years actually provide all the energy humanity needs? It's a question that sounds almost too good to be true, doesn't it? Like something from a particularly optimistic science fiction novel. But as we'll discover together in the gentle darkness of this evening, the mathematics of sunlight are far more generous than most of us ever imagine. The sun, that reliable companion that rises each morning and sets each evening, is actually showering us with more energy in a single hour than humanity uses in an entire year. But before we dive deep into the golden mathematics of photons and efficiency rates, I want you to do something for me. If you can, take a moment to think about sunlight, not as a scientific phenomenon, not as electromagnetic radiation or fusion reactions, but simply as the warm touch you feel on your skin when you step outside on a bright day. That gentle heat, that soft pressure of light on your face, it's been the same sensation felt by every human who has ever lived. The same photons that warmed the faces of ancient astronomers as they mapped the heavens, the same solar energy that powered the first plants to emerge from primordial seas. This video is, as always, designed for educational and relaxation purposes, and while I hope it fills you with wonder about our solar future, I certainly don't want it to keep you awake with excitement. Though if it does, well, at least you'll have learned something fascinating about the most abundant energy source in our cosmic neighborhood. So settle back, let your breathing slow, and join me as we follow the path of sunlight from nuclear fusion to silicon cells, from laboratory dreams to global possibilities. Because tonight, we're going to discover that the question isn't really whether the sun can power our world, but rather whether we can build the technology elegant enough to catch its generous gift. The story begins, as so many stories do, with fire. But this isn't the flickering flame of a candle or the crackling warmth of a fireplace. This is a fire that burns without oxygen, a nuclear furnace so vast and so intense that it could fit more than 1,000,000 Earths inside it, and still have room for more. This is our sun, and understanding its power is the first step in our gentle journey towards solar possibilities. Deep in the sun's core, where the temperature reaches 15 million degrees Celsius, something remarkable happens every single second. Hydrogen atoms, the simplest and most abundant element in the universe, are crushed together under such immense pressure that they overcome their natural electrical repulsion and fuse together to create helium. It's a process called nuclear fusion, and it's been happening reliably for about 4.6 billion years. Each time 4 hydrogen atoms fuse to create 1 helium atom, a tiny amount of mass disappears, converted directly into energy according to Einstein's famous equation E=mc². That little c in the equation, that's the speed of light, and it's squared, which means even a tiny amount of mass becomes an enormous amount of energy. The sun converts about 4 million tons of matter into pure energy every single second, and this energy radiates outward in all directions as light, heat, and other forms of electromagnetic radiation. Now you might be thinking, 4 million tons every second sounds like a lot. Won't the sun eventually run out? It's a wonderfully practical concern, and the answer is both reassuring and mind-boggling. The sun is so massive, containing about 99.86% of all the mass in our solar system, that even at this seemingly extravagant rate of consumption, it has enough hydrogen fuel to continue shining steadily for another 5 billion years. That's longer than Earth has existed, longer than life has been evolving on our planet, longer than our species can probably even imagine. But here's what makes this solar story even more remarkable. Of all that energy radiating out from the sun in every direction, only about 1 part in 2 billion actually hits our planet. We're essentially catching just the tiniest fraction of the sun's output, like trying to catch raindrops in a teacup during a thunderstorm. And yet even this tiny fraction represents an almost incomprehensible amount of power. The energy that reaches the top of Earth's atmosphere is approximately 1,361 watts per square meter. Scientists call this the solar constant, though it varies slightly as Earth's orbit carries us closer to or farther from the sun throughout the year. To put this in perspective, imagine covering every square meter of the Earth's surface with about 14 100-watt light bulbs, all burning continuously. That's roughly the amount of solar energy our planet intercepts every moment of every day. Of course, much of this energy never makes it to the ground. Our atmosphere, that thin blanket of gases that keeps us alive, also acts as a filter for incoming sunlight. Clouds reflect some energy back to space. The atmosphere absorbs some, and various particles scatter light in all directions. On a clear day, perhaps 70% of the solar energy that hits the top of our atmosphere actually reaches the surface. On a cloudy day, that percentage drops significantly. But even accounting for atmospheric losses, seasonal variations, and the simple fact that it's nighttime on half the planet at any given moment, the amount of solar energy reaching Earth's surface is staggering. Every hour, our planet receives approximately 120,000 terawatts of solar energy. To put that number in context, total global energy consumption, everything from the electricity that powers cities to the fuel that moves ships across oceans, amounts to about 18 terawatts. This means that in just 1 hour, the sun delivers about 6,600 times more energy to Earth than all of humanity uses. In 1 day, we receive enough solar energy to power current global civilization for 27 years. And this delivery happens every single day reliably, without fail, powered by nuclear fusion reactions that will continue for billions of years to come. It's a number so large that it almost loses meaning, like trying to count the stars or imagine the size of the universe. But perhaps that's exactly the point. The sun's generosity is so vast that our challenge isn't whether there's enough energy available, but whether we can develop the technology and infrastructure to capture even a tiny fraction of what's freely offered every day. The mathematics of solar abundance paint a picture that seems almost too good to be true, but numbers, as comforting as they might be, are only part of the story. The real question becomes, how do we catch sunlight and turn it into electricity? How do we transform photons, those massless particles of light, into the kind of energy that can power our homes, charge our devices, and run our civilization? The answer lies in one of the most elegant discoveries of the 20th century, a phenomenon so fundamental to modern life that we often take it for granted: the photovoltaic effect. It's the process by which certain materials can convert light directly into electricity, and understanding it requires us to venture into the strange and wonderful world of quantum physics, where light behaves like both a wave and a particle, and electrons can be knocked loose by nothing more than a gentle touch of sunlight. The story begins in 1839 with a young French physicist named Alexandre Edmond Becquerel. He was working in his father's laboratory, experimenting with electrochemical cells when he made a curious observation. When light struck certain materials, they seemed to generate a small electric current. It was a phenomenon so subtle that it might have been dismissed as experimental error. But Becquerel was careful and methodical. He had discovered the photovoltaic effect, though he didn't fully understand what he was seeing. For decades, the photovoltaic effect remained little more than a scientific curiosity. Researchers could demonstrate it, measure it, and even improve it slightly, but the efficiency was so low, and the cost so high, that it seemed destined to remain a laboratory novelty. It wasn't until the 1950s that scientists at Bell Labs, working with silicon crystals, created the first practical solar cell with an efficiency of about 6%. To understand how a solar cell works, imagine silicon as a crystal lattice, a perfectly ordered arrangement of atoms sharing electrons in a stable, predictable pattern. Pure silicon is actually not very useful for solar cells because all its electrons are happily locked in place, content to stay where they are. But if you introduce tiny amounts of other elements, a process called doping, you can create imbalances that make the silicon much more interesting. On one side of a solar cell, silicon is doped with elements like phosphorus, which have extra electrons. This creates what's called N-type silicon, where N stands for negative because of all those surplus electrons looking for somewhere to go. On the other side, silicon is doped with elements like boron, which create holes where electrons should be. This is P-type silicon, where P stands for positive because of all those empty spaces that electrons would love to fill. When you sandwich these two types of silicon together, something magical happens at the boundary between them. Electrons from the N-type side start migrating toward the holes in the P-type side, but only up to a point. Eventually, the migrating electrons create an electric field that prevents further movement. The result is a stable boundary layer, with a built-in electric field, just waiting for something to disturb the balance. That something is sunlight. When a photon of light strikes the silicon with enough energy, it can knock an electron loose from its normal position, creating what physicists call an electron-hole pair. The built-in electric field immediately pushes the free electron toward one side of the cell, and the hole toward the other. Connect wires to both sides, and you have electricity flowing through a circuit. It's that simple. And that elegant light goes in. Electricity comes out. Of course, the reality is more complex than this gentle explanation suggests. Not all photons have the right amount of energy to free electrons. So much of the sunlight that hits a solar cell simply passes through or gets converted to heat. Early solar cells were quite inefficient, converting only a small percentage of incoming light into electricity. But over the decades, through careful research and engineering, efficiencies have steadily improved. Modern silicon solar cells in commercial production typically achieve efficiencies between 18% and 22%. Meaning they can convert about 1/5 of the sunlight that hits them into electricity. Laboratory demonstrations have achieved even higher efficiencies, sometimes exceeding 26% for silicon cells and over 40% for more exotic multi-junction cells that use several different materials to capture different portions of the solar spectrum. But efficiency, while important, isn't the only consideration. Cost matters enormously, as does reliability, durability, and the ability to manufacture solar cells at scale. And this is where the solar story becomes particularly encouraging. Over the past 4 decades, the cost of solar photovoltaic systems has dropped by more than 99%, making solar electricity competitive with conventional power sources in many parts of the world. This dramatic cost reduction has been driven by improvements in manufacturing, increases in scale, and the kind of learning by doing that happens when an industry grows rapidly. Each doubling of cumulative solar panel production has historically led to a roughly 20% decrease in cost, a phenomenon so reliable that it has its own name, Swanson's Law, after Richard Swanson, the founder of SunPower. Today, in many sunny regions of the world, new solar installations can generate electricity more cheaply than coal, natural gas, or nuclear plants. In some locations, solar has become the cheapest source of electricity in human history, and unlike fossil fuel plants, once a solar installation is built, the fuel, sunlight, is free for the lifetime of the system, typically 25 knots, 30 years or more. The transformation has been so rapid and so complete that it has surprised even experts who have been following the industry for decades. In 2000, total global solar capacity was measured in megawatts, enough to power perhaps a few small towns. Today, global solar capacity exceeds 1,000 gigawatts, enough to power hundreds of millions of homes. The growth has been exponential, doubling every few years, driven by falling costs and increasing recognition of solar's potential. But raw capacity numbers, impressive as they might be, don't tell the complete story of whether solar can truly power the world. To understand that possibility, we need to examine not just how much solar energy is available and how efficiently we can capture it, but also the practical challenges of turning intermittent sunlight into reliable electricity that can power everything from smartphones to steel mills. The challenge with solar energy isn't abundance, as we've seen. The sun provides far more energy than we could ever use. The challenge is timing and consistency. The sun shines during the day but not at night. It shines brightly on clear days but dimly through clouds. Solar output varies with the seasons, with geography, and with weather patterns that can change from hour to hour. This variability has led to what energy experts call the intermittency problem. Traditional power plants, whether they burn coal, split uranium atoms, or harness flowing water, can generally be turned on or off as needed to match electricity demand. But solar panels produce power when the sun shines, not necessarily when people need electricity most. In many places, peak electricity demand occurs in the evening when people come home from work, turn on lights, cook dinner, and watch television, but that's precisely when solar panels stop producing power. For decades, this intermittency was seen as solar power's fatal flaw, the reason why it could never be more than a niche source of electricity. Critics argued that you would always need backup power plants running on fossil fuels to provide electricity when the sun wasn't shining. Solar might be a nice supplement to the grid, they said, but it could never be the foundation. But two developments have dramatically changed this calculation. First, electricity consumption patterns have evolved. With more efficient appliances, LED lighting, and the growth of electric vehicles that can charge during the day when solar production peaks, demand patterns are gradually shifting toward daylight hours. Second, and perhaps more importantly, energy storage technology has advanced rapidly, making it increasingly practical to store solar energy generated during the day for use at night. The most visible symbol of this energy storage revolution has been the lithium-ion battery, originally developed for consumer electronics and later adapted for electric vehicles. Lithium-ion batteries have experienced their own dramatic cost reductions and performance improvements. Between 2010 and 2020, the cost of lithium-ion battery packs fell by nearly 90%, while energy density improved substantially. Today, massive battery installations are being built alongside solar farms, creating what the industry calls solar plus storage systems. These installations can generate electricity during the day, store excess energy in batteries, and then release that stored energy in the evening when demand peaks. Some of these battery installations are enormous. The Hornsdale Power Reserve in Australia, for example, can store 193 megawatt-hours of energy, enough to power approximately 30,000 homes for an hour. But batteries are just one approach to the storage challenge. Pumped hydro storage, where excess solar electricity is used to pump water uphill during the day and then released through turbines to generate electricity at night, remains the most common form of grid-scale energy storage worldwide. Compressed air energy storage, where excess electricity powers compressors that pump air into underground caverns, offers another pathway. Even more exotic approaches, like using excess solar electricity to produce hydrogen through electrolysis, and then burning that hydrogen later to generate power, are being explored. The storage landscape is evolving so rapidly that what seemed impossible just a decade ago now seems not just possible, but inevitable. Multiple studies by energy researchers have concluded that combinations of solar generation and various storage technologies could reliably provide electricity around the clock, even in locations that experience significant seasonal variations in sunlight. Perhaps even more promising is the idea of geographic diversity. While it might be cloudy and calm in one location, it's likely sunny and windy somewhere else. A highly connected electrical grid could transport renewable energy from wherever it's being generated to wherever it's needed. During the day, electricity could flow from solar-rich regions to areas where demand is high. At night, the flow could reverse, with stored energy or power from different time zones supplying electricity where the sun has set. This vision of a globally connected renewable energy system is already beginning to take shape. Underwater cables carry wind-generated electricity from offshore wind farms to population centers. High-voltage transmission lines, transport solar power from desert installations to distant cities. As transmission technology improves and costs fall, these connections will become longer and more numerous, creating what some experts envision as a global energy internet. The technical challenges of intermittency, while still significant, are increasingly looking like engineering problems with known solutions rather than fundamental barriers. And as solar costs continue to fall and storage technologies improve, the economic case for a solar-powered world becomes stronger every year. But even if solar energy can be stored and transmitted efficiently, can it really scale up enough to power everything? Can we build enough solar panels and batteries and transmission lines to replace all the coal plants and gas plants and oil refineries that currently fuel our civilization? The scale required is certainly daunting. Current global electricity generation capacity is approximately 8,000 gigawatts. To replace all fossil fuel power plants with solar would require roughly 13,000 to 15,000 gigawatts of solar capacity, accounting for capacity factors and inefficiencies. That represents about a 15-fold increase from current global solar installations. But here's where the math becomes encouraging again. If global solar installations continue to grow at their current rate, doubling roughly every 3 years, we would have enough solar capacity to generate all the world's electricity within about 12–15 years. Of course, sustained exponential growth is difficult to maintain indefinitely, but even if growth rates slow significantly, a primarily solar-powered electricity system appears achievable within a few decades. The land requirements, while substantial, are manageable. Various studies have calculated that powering the entire world with solar energy would require somewhere between 190,000 and 400,000 square kilometers of land, depending on assumptions about efficiency and capacity factors. That sounds enormous, until you realize it represents only about 0.13% to 0.27% of the world's total land area. It's roughly equivalent to covering an area the size of Nebraska with solar panels, which seems quite reasonable for powering the entire planet. In practice, much of this solar capacity wouldn't require dedicated land at all. Rooftop solar installations, solar panels over parking lots, floating solar arrays on reservoirs and other water bodies, and agrivoltaics, solar panels integrated with agriculture, could provide substantial amounts of electricity without competing with other land uses. The combination of distributed rooftop installations and larger utility-scale solar farms could comfortably provide all the electricity humanity needs. The manufacturing capacity required would certainly be substantial. Currently, global solar panel manufacturing capacity is approximately 300–400 gigawatts per year, and growing rapidly. To reach the scale required for a fully solar-powered electricity system, manufacturing capacity would need to increase by perhaps another order of magnitude. But this seems achievable given the industry's track record of rapid expansion and the increasing number of countries and companies investing in solar manufacturing. Materials availability presents some constraints, but not insurmountable ones. Silicon, the primary material in most solar panels, is the second most abundant element in Earth's crust. Silver used for electrical contacts in solar cells is scarcer and more expensive, but researchers are developing techniques to reduce silver consumption or replace it with more abundant materials like copper. Lithium for batteries is currently mined in only a few locations, but reserves are substantial and recycling technologies are improving rapidly. The financial investment required would be massive but not unprecedented. Various estimates suggest that fully transitioning global electricity generation to renewables would require investment on the order of $100, $200 trillion over several decades. That sounds staggering until you consider that the world already spends approximately $6 trillion per year on energy. Much of the renewable transition could be financed simply by redirecting current energy investment from fossil fuel infrastructure to renewable systems. Moreover, unlike fossil fuel systems, renewable energy systems have very low operating costs once built. Solar panels and wind turbines don't require fuel purchases, and their maintenance requirements are relatively minimal. Over their lifetime, Renewable energy systems typically generate electricity at lower total cost than fossil fuel alternatives, meaning the higher upfront investment pays for itself through lower operating expenses. The transition would certainly face challenges beyond pure technical and economic considerations. Political inertia, regulatory barriers, entrenched interests in fossil fuel industries, and the simple difficulty of coordinating change across different countries and jurisdictions all present obstacles. But the fundamental conclusion remains striking. From a purely technical and resource perspective, solar energy appears capable of powering human civilization many times over. Perhaps most encouraging is that we don't need to solve the entire problem at once. Each solar panel installed, each battery system deployed, and each mile of transmission line built makes the overall system a little more renewable, a little more resilient, and a little less dependent on fossil fuels. The transition can be gradual, market-driven, and adaptive to local conditions and constraints. But electricity, important as it is, represents only part of humanity's total energy consumption. We also use enormous amounts of energy for transportation, heating buildings, and industrial processes like making steel and cement. Can solar energy handle these needs as well, or is its potential limited to generating electricity? This question opens up fascinating possibilities that extend far beyond solar panels on rooftops. Solar energy's potential to reshape our entire energy system becomes even more intriguing when we consider how electricity might replace other forms of energy consumption. Transportation, which currently consumes about 27% of global energy, mostly in the form of gasoline, diesel, and jet fuel, is already beginning its transition to electricity. Electric vehicles, once expensive curiosities, are rapidly becoming cost-competitive with conventional cars. Battery costs have fallen so dramatically that electric vehicles are approaching price parity with gasoline cars, even before considering lower operating and maintenance costs. The logic is compelling. An electric vehicle powered by solar electricity is essentially running on sunlight. Instead of drilling for oil, refining it into gasoline, and burning it in an internal combustion engine, a process that wastes about 70 to 80% of the original energy, we can capture sunlight directly and use it to move vehicles with much higher efficiency. Electric motors convert about 90% of their electrical input into motion, compared to roughly 20 to 30% efficiency for internal combustion engines. The same principle applies to heating buildings. Instead of burning natural gas or oil for heat, we can use solar-generated electricity to power heat pumps, which can provide 3 to 4 units of heat for every unit of electricity consumed. Even in cold climates, modern heat pumps can efficiently extract heat from outside air and concentrate it inside buildings. The combination of solar electricity and heat pump technology could eliminate most fossil fuel consumption for space heating. Industrial processes present more complex challenges but also remarkable opportunities. Making steel, producing cement, refining aluminum, and manufacturing chemicals currently require enormous amounts of energy, often in the form of high-temperature heat that's difficult to generate with electricity. But researchers are developing new approaches: electric arc furnaces for steel making, solar thermal concentrators for high-temperature industrial processes, and even the use of solar-generated hydrogen as a fuel and chemical feedstock. Hydrogen, in particular, offers a pathway for solar energy to penetrate sectors that are difficult to electrify directly. Excess solar electricity can power electrolysis systems that split water into hydrogen and oxygen. The hydrogen can then be stored, transported, and used as a fuel for shipping, aviation, and industrial processes that require high energy density or high temperatures. Japan, South Korea, and several European countries are already investing heavily in what they call the hydrogen economy, envisioning hydrogen as a way to store and transport renewable energy over long distances and time periods. The potential is staggering when you add up all these applications: transportation, powered by solar electricity, buildings heated by solar-powered heat pumps, and industries running on solar-generated hydrogen could eliminate the vast majority of fossil fuel consumption. Some studies suggest that renewable energy, primarily solar and wind, could provide 80 to 90% of total global energy needs, not just electricity, by mid-century. Of course, such a transformation would require massive changes in infrastructure, technology, and social systems. Electric vehicle charging networks, hydrogen distribution systems, updated electrical grids, and retrained workforces would all be necessary. The technical challenges are substantial, and the coordination required would be unprecedented in human history. But perhaps most remarkable is how many of these changes are already underway. Electric vehicle sales are growing exponentially in many countries. Heat pump installations are increasing rapidly as costs fall and performance improves. Industrial companies are investing in pilot projects for solar-powered manufacturing. Governments are setting ambitious renewable energy targets and providing financial incentives for the transition. The momentum building behind renewable energy, and solar energy in particular, feels different from previous energy transitions. It's not being driven primarily by government mandates or environmental concerns, though those factors matter. Instead, it's increasingly driven by simple economics. Renewable energy is becoming the cheapest option for new power generation in more and more markets around the world. This economic logic is powerful because it's self-reinforcing. As more solar panels are manufactured, costs fall further due to economies of scale and learning effects. As more renewable energy comes online, fossil fuel plants become less profitable and are retired earlier than planned. As storage costs fall, the intermittency challenge becomes less significant. Each development makes the next step easier and more economically attractive. The result is what economists call a positive feedback loop, where success breeds more success. We may be approaching what some researchers describe as a tipping point, where renewable energy becomes so cost-effective that the transition accelerates under its own momentum, regardless of policy interventions or environmental concerns. But even if solar energy can theoretically power the world, and even if the economics are becoming increasingly favorable, significant challenges remain. These aren't technical barriers so much as social, political, and institutional obstacles that could slow or complicate the transition. One of the most significant challenges is simply the scale of the transformation required. The global energy system represents trillions of dollars in existing infrastructure, power plants, refineries, pipelines, transmission lines, vehicles, and buildings. Much of this infrastructure is relatively new and still has decades of useful life remaining. Stranding these assets prematurely would impose enormous costs on their owners, who naturally resist such outcomes. The fossil fuel industry, understandably, has little enthusiasm for a transition that would eliminate most of their business. Oil and gas companies have responded with a variety of strategies. Some are investing in renewable energy and positioning themselves as energy companies rather than specifically fossil fuel companies. Others are focusing on applications where fossil fuels may remain competitive longer, like petrochemicals and long-distance shipping. And some are simply fighting the transition through political lobbying and public relations campaigns. These political and economic conflicts play out differently in different countries. Nations with large fossil fuel resources may resist the transition because it would reduce the value of their natural endowments. Workers in coal mines, oil fields, and related industries may oppose changes that threaten their livelihoods. Local communities that have built their identities and economies around fossil fuel extraction may view renewable energy as an existential threat. The international dimensions of the energy transition add further complexity. Currently, fossil fuels are traded globally, creating economic relationships and dependencies between producer and consumer nations. A world powered primarily by renewable energy would have very different geopolitical dynamics. Countries with abundant sunshine and wind would gain influence, while traditional energy exporters might find their strategic importance diminished. These challenges aren't insurmountable, but they do suggest that the transition to solar energy won't be simply a matter of technology and economics. It will require careful attention to social equity, just transition policies for affected workers and communities, and diplomatic efforts to manage international tensions. There are also legitimate technical questions that remain unresolved. While renewable energy with storage can provide reliable electricity, the exact mix of technologies and the optimal system design are still being debated and refined. Grid stability, with high renewable penetration, requires sophisticated management systems and possibly new approaches to electricity markets and pricing. Long-term storage remains challenging and expensive, particularly for covering extended periods of poor weather or seasonal variations in solar availability. While batteries can handle daily cycling, storing solar energy generated in summer for use in winter requires different technologies that are still being developed and tested. The reliability requirements for critical infrastructure, like hospitals and military installations, may require backup systems even in a primarily renewable grid. Some industries with continuous high-temperature processes may find it difficult to operate solely on intermittent renewable power, at least with current technology. These technical challenges are receiving intense research attention, and solutions are emerging rapidly, but they serve as reminders that transitioning to a solar-powered world is a complex engineering and social challenge, not simply a matter of installing more solar panels. Despite these challenges, the trajectory seems clear. Solar energy costs continue to fall, efficiency continues to improve, and deployment continues to accelerate. Storage technologies are advancing rapidly, and system integration challenges are being addressed through smart grid technologies and sophisticated control systems. Perhaps most importantly, the vision of a solar-powered world is no longer the fantasy of environmental activists or the speculation of science fiction writers. It's increasingly the working assumption of energy planners, utility companies, and government agencies around the world. Major consulting firms, international energy agencies, and investment banks are all projecting scenarios where renewable energy, led by solar, provides the majority of global electricity within a few decades. The question is no longer whether solar energy can power the world, but how quickly the transition will happen and what the pathway will look like. Will it be a gradual evolution spanning several decades, or will technological breakthroughs and policy changes accelerate the timeline? Will different regions follow different paths, or will global coordination create a more uniform transition? These questions remain open, but the fundamental conclusion seems increasingly clear. The sun provides far more energy than humanity could ever use. Our technology for capturing that energy is rapidly improving and becoming more cost-effective, and the engineering challenges of building a solar-powered civilization appear manageable with known approaches and continued innovation. In a sense, we're returning to our roots. For most of human history, civilization was powered directly or indirectly by solar energy. Food crops converted sunlight into chemical energy. Wood burning released solar energy stored in trees, and wind patterns driven by solar heating provided power for sailing ships and windmills. Fossil fuels represented a detour, a way of accessing ancient solar energy that had been stored underground for millions of years. Now we're developing the technology to access solar energy directly and immediately, without the need for geological storage processes or the environmental consequences of burning fossilized sunshine. In a sense, solar power represents not a new energy source, but a return to the original source that has always powered life on Earth. This perspective provides a certain philosophical comfort. We're not trying to harness exotic new forces or develop fundamentally new physics. We're simply getting better at catching the energy that has been raining down on our planet every day for billions of years. The sun has been powering Earth's biosphere since complex life began, and with the right technology, it can power human civilization as well. The story of solar energy is still being written, but the chapters we can already see suggest a narrative of abundance, ingenuity, and possibility. It's a story about learning to live within the energy budget that nature provides rather than depleting finite resources. It's about technology that becomes more powerful and less expensive over time rather than more costly and more complex. Most of all, it's a story about hope. In a world facing climate change, air pollution, and the eventual depletion of fossil fuel resources, solar energy offers a pathway toward a cleaner, more sustainable, and ultimately more prosperous future. It's a reminder that some of our biggest challenges may have surprisingly elegant solutions, and that the universe may be more generous than we sometimes dare to imagine. As you settle into sleep tonight, perhaps you'll think about the sunlight that warmed your skin today, the ancient fusion reactions still occurring in the sun's core, and the photons that will arrive tomorrow morning carrying enough energy to power human civilization many times over. The sun rises every day, reliable as clockwork, generous beyond measure, offering us more energy in a single hour than we know what to do with. The question isn't whether the sun can power our world. The question is whether we'll be wise enough and creative enough to accept its gift, and based on the remarkable progress of the past few decades, that answer seems to be a resounding yes. Sweet dreams, and may your tomorrow be as bright as the promise of solar energy itself.